Okay, let's look at this November 2015 electricity question. Here are the formulas for electricity. Obviously this one is the one that I like to use, but these are the ones that are on your data sheet. So, two identical light bulbs, A and B, as well as a measuring device Z, are connected to a battery as shown in the circuit below. The switch is initially open. What physical quantity will device Z measure when the switch is closed? Okay, so this device Z is in series. So if it's in series, it has to be an ammeter. What do ammeters measure? They measure current. Give a reason why the brightness of the bulbs will be the same when the switch is closed. Okay, so first of all, the bulbs are identical. Show them that you can get the correct information out of the question paper. So if you state that you know that the bulbs are identical, okay, then you say current is the same everywhere in a series circuit. So the same current flows through the two bulbs, delivering the same amount of energy to make them shine equally. You can say something like that. The key points are like to mention that the bulbs are identical and the current is what's making them shine and the current is the same everywhere. Now it says to you a third identical bulb is connected in series with bulbs A and B. Will the brightness of the bulbs increase, decrease, or remain the same? What are we doing to the circuit? If we add another bulb, it's a series circuit. We are increasing the resistance. The moment you increase the resistance, the current decreases. So this bulb is going to shine less brightly because it's got less current going through it. Okay, now let's look at this question here below. This question's a little bit more interesting. In the circuit below, potential difference V1 across the battery and potential difference V2 across the 4 ohm resistor are unknown. When switch S is closed briefly, the potential difference across the parallel combination is 4 volts. So we know that these two parallel resistors have got a resistance of 4 volts, but we don't know this voltage, a resistance of 4 volts, a potential difference of 4 volts. But we don't know this voltage and we don't know that voltage. Then it says to you, define the potential difference, define the term potential difference. So there's a couple of definitions in the memo. When you check the memos, just check them against your exam guidelines. The exam guidelines are what chooses if you've got the correct definition or not. So in the exam guidelines, and it says the energy transferred per unit electric charge flowing through the ends of a conductor. So this is the definition you want to use. We need the per unit charge, we need the conductor, and we need, of course, the energy. So it's the energy per unit charge flowing through a conductor. Now it says to you, calculate the effective resistance of the 2 and the 6 ohm resistors. So these two are in parallel, okay? So you can use the formula R parallel, 1 over R parallel equals 1 over R1 plus 1 over R2. And then you find the answer and you invert it, okay? So you would have a half plus a sixth, and then you invert that. I'm going to use the other formula, the product times the product of the resistors over the sum of the resistors. So this is 2 times 6 is 12. Okay, so R parallel is going to be equal to 12 divided by 8. So my parallel resistance is going to be 1.5 ohms. No unit, no mark. Okay, so this is my parallel resistance. Now it says to you, calculate the reading on voltmeter 1. Now voltmeter 1 is the total voltage in the circuit. So if you look at this circuit and you take these two resistors and you consider them as 1.5 ohm resistor. This is why we've calculated the effective resistance. So then if we look at this circuit, we pretend this is a 1.5 ohm resistor and we have this as a 4 ohm resistor. So the total potential difference in this circuit, this V1 will be equal to this 4 volts plus V2, okay, because a series circuit is a potential divider. So we just pretend these two parallel resistors are a single 1.5 ohm resistor. That's why we call it the effective resistance. And now we can use the ratio calculations, okay. So if we look at the ratio of the resistances, these two have an effective resistance of 1.5 ohms, and this one has a resistance of 4 ohms, okay. So the total is going to be, the total of my ratio, okay, is going to be 1.5 plus 4 is 5.5. So if we have a look here, we know that 1.5, okay, over, because now I'm looking at the parallel resistors, 1.5 over 5.5 is going to be equal to, where's my equal sign, the 4 volts over the total voltage on V1, okay, because remember, my total voltage in the system is going to be these two voltages added together, because this is a series circuit that divides the potential, okay. So the total of the ratio is 5.5, and this 4 volts is how much potential has gone through, is over these two resistors, and these two have a resistance of 1.5. So this is a lot easier to see if it's as a fraction. So imagine this as 1.5 over the total of the ratio, which is 5.5, is equal to 4 volts over the total resistance and the total potential of the circuit. It's so irritating trying to keep these words straight in your mouth. Okay, so if we have a look here, we can now do algebra with this, okay. V1's on the bottom, so it's going to be 4 over those other values. And if you put that into your whole calculator, and you can run your calculator properly, you're going to get 4,6666667. So we just call it 14,67 volts, and that will be your final answer. Okay, so you can do a whole complicated thing as well, as you can say, okay, you can work out the current and a whole bunch of stuff, but this is actually the easier way, is to know that this circuit is a voltage divider. You pretend this is a series resistor, and then you work it out using ratios, okay. So then if we want to calculate the reading on voltmeter 2, if we know that this is 14,67 and we know that this is 4, then the reading on voltmeter 2 has to be what's left. So it's going to be 14,67 minus 4, which is going to be 10,67 volts. What we should actually do here, okay, what we should do here is that we should actually describe what we're doing, okay. So V total, or we can call it V1, because look, it's V1 in the question. V1 equals 4 volts plus V2. Okay, so what we're saying is the total potential is equal to the potential over the parallel plus the potential over the series. And then you just do the sum, and there we have our 2 marks for that part of the sum. And this question is complete.